Good evening, Laman. Today we are going to discuss about the isomers, isomerism. Right. So first, let's discuss what these isomers are, or what this concept is. The isomerism concept is. Right. The isomerism is the existence of different compounds, but with the same molecular formula. The same molecular formula, the existence of the different compounds are referred to as the isomerism. Then what are the isomers? Those compounds are referred to as isomers. The compounds with the same molecular formula but differs with their structure or with the three-dimensional arrangement. Anyway, different compounds with same molecular formula are referred to as isomers. Existence of such compounds are referred to as the isomerism. Right? Okay, let's go to the definition which is appearing in your cute. See, it says isomerism. Isomerism is the existence of different compounds but with the same molecular formula. Different compounds having the same molecular formula are called isomers. Now, we have such two kinds of isomers. Isomers are categorized, right, under two sections, right? Two kinds of isomers are there. What are the two kinds? Let's discuss one by one, right? So, even though your molecular formula is the same, there could be different compounds varying due to their structural arrangement, they had the atomic connectivity, or due to their 3D arrangement of atoms in space. Right? Those are the two reasons for molecules to differ, even though those are with same molecular formula, right? So those are referred to as the two kinds, constitutive isomers and the stereoisomers. So constitutive isomers are the isomers which differs due to changes in the structure, or one can say changes in the atomic connectivity. Which is referred to as structure. Changes in structure. So that the constitutional isomers are also known as structural isomers. Sometimes the same thing is also known as structural isomers. Right? Actually, we are with such three kinds. Right? We are with such three kinds. Right? Number one, chain isomers or chain isomerism. Due to the difference of the main carbon chain, this isomerism appears. And position isomers, And the third kind is functional group isomers. Right? We'll discuss these things further, right, when we are discussing about the structural isomers, right? Okay. So 3 kinds of constitutional law structural isomers are there. Then the stereoisomers. What are these? Stereoisomers are the isomers. Stereoisomers are the isomers which differs due to 3D arrangement in space. Due to 3-dimensional arrangement of atoms in space. It is important to note that with these isomers, the structure won't change. Note that the atomic connectivity, the structure of the atomic connectivity, won't change. The structure won't change. Right? The same atomic connectivity, but if the atoms are arranged differently in 3D space, such situations are referred to as stereoisomers. Right? If you need some example, so like this. So as examples, so these two are some examples for stereoisomerism. Right? See, this one and this one. So even though the atomic connectivity is same with these two guys, these are 2 different compounds. Why is that? Their 3D arrangement differs. The atomic connectivity is same, Laman. See, if you are to think of this carbon that is connected to 1 hydrogen and 1 bromine and to a double bond, right? When it comes to this carbon, you are with a hydrogen, Br and a double bond. If you think of the other carbon, see this carbon, it is the hydrogen, Br and a double bond. If you think of the other carbon, the same thing. Right? Both are carrying the same atomic connectivity. So we say the structure is the same. With these guys, structure is the same. Right? Structure means the atomic connectivity is the same. Right? But you clearly see the 3D arrangement of atoms differ. If you are thinking of this structure, right? If you are thinking of this structure, the 2 hydrogens are located like this, but here the hydrogens are located diagonally. But here at the same side of the double bond, if you have to come up with a line like that, at the same side of the double bond, you can see the 2 hydrogens. But here diagonal relationship is there. With the bromines as well, same thing appears. So 2 different molecules with the same atomic connectivity. The reason for to differ is actually the arrangement of atoms in 3D space, right? So such compounds are referred to as stereoisomers. Structure is the same, but 3D arrangement of atoms in space differs. Right? So those are some examples for the stereoisomers. Right? Okay. So when it comes to stereoisomers, Lamai, so we'll learn these things further. But as a sketch, as a summary, I'll introduce the two types of stereoisomers as well with this section. Right? When it comes to stereoisomers, right, those are of two types. What are the two types? Right? One kind is enantiomers or enantiomerism. Enantiomers. The second kind is diastereomers or the diastereism. Right? Enantiomers and the diastereomers. Enantiomers and the diastereomers. Right? The two kinds. Right? Okay. We'll discuss about these two kinds. Enantiomers. Enantiomers are the compounds which are mirror images of each other. So enantiomers are stereoisomers which are mirror images of each other. So I'll give you an example here. Right? See. If you are taking this one, and its mirror image like this, with these two compounds, both are with the same atomic connectivity. So that these are stereoisomers. With this carbon, you have a hydrogen, bromine, chlorine and fluorine connected. With this one, the same. Right? Both are the same atomic connectivity. But they differ with the arrangement of atoms in 3D space. Right? It is like, right, the two hands of you. Right? So one can say the one palm of you is the mirror image of the other palm. Right? So if you take this one hand like this, right, that will be the mirror image of the other hand. Right? Left hand is the mirror image of right hand. Those are mirror images. The connectivity is the same. But those are two different things, right? You can't superimpose this guy with this one. Superimpose means you can't put the same thing at the same space as the earlier. This is what is meant by superimposing. So you can't superimpose the two, right? At the same space occupied by the other's left hand can't be taken by the right hand. So one can say you can do that by representing like this. So that is not the case, right? So if the palm is towards you, right? With this one as well, the palm is towards you. So you can't superimpose like this. So you can't, no? Won't connect, right? Okay. So you can't superimpose the two guys. So two different things there, right? So the two mirror images are two different compounds, right? So such situations, the atomic connectivity is same, the connectivity is same. The thumb is connected to the index finger with this one as well. The index finger is connected to beside the index finger, you can see the appearance of the middle finger as well as thumb. With this one as well, same thing, right? Okay. So but those are two different things, right? So such stereoisomers are referred to as enantiomers. Atomic connectivity is same, and the other compound is the mirror image of the considering compound. Such situation, the two guys are considered as enantiomers. Enantiomers, right? So basically, to show the enantiomism, there is a requirement for your molecule to fulfill. The requirement is you should have a chiral carbon. You should have a chiral carbon with you. You should have a chiral carbon with you, right? Chiral carbon with you. Chiral carbon. What this means? A chiral carbon means a carbon with 4 different groups attached to it. A carbon with 4 different groups attached to it is referred to as a chiral carbon, right? That chiral word came from the Greek word for the hand, right? The chiral symmetry, right? That is why this is named as chiral, right? So chiral carbon, or one can say the asymmetric carbon, both names are used. Right? So if you are with a chiral carbon or asymmetric carbon, that means a carbon with 4 different groups attached to it, then such compounds are able to show the enantiomism. That compound and its mirror image are two different compounds, right? So that is all about the enantiomism, enantiomers, right? Let's discuss about the other kind of stereoisomers. The second kind. The second kind, right, is referred to as the diastereomers. So what is the definition there? The definition of the diastereomers is like this. The stereoisomers, that means the atomic connectivity should be the same, only differs with the 3D arrangement in space of the atoms, right? So stereoisomers which are not the mirror image of each other, which are not the mirror images, of each other. Those are diastereomers. So if you need an example, right, earlier example, right, what we had discussed, right? So these two guys are actually diastereomers, right? This one and this one, these are not the mirror images of each other, right? Atomic connectivity is same, but not the mirror image of each other, right? So you can't, this is not the mirror images, no? Right? If you have a mirror here, the same distance should appear, no? With the guys. This is okay, but not with these, no? distance is different. This distance, yeah, this one is not gas, right? So these are two compounds, stereoisomers, with the same atomic connectivity. So, but differs with the 3D, but differs with the 3D arrangement, right? That is why we call these guys as stereoisomers. But these are not mirror images for each other. So these are referred to as, right, diastereomers. Stereoisomers which are not the images of each other, right? No? So it comes to diastereomers, we have two types. Diastereomers are of two types. One kind is the geometric isomers. Some other kinds are also there. We are not going to discuss about the other kinds of diastereoism in our lectures, but geometric is further studied. When it comes to geometric isomerism, also we have two types: cis-trans and cis-trans isomerism, and so we have some other kind as EZ system, EZ diastereoism, but let's take it as other because not further studied under A-level syllabus, right? So this is free for the isomers, right? So let's discuss about all of these stuff one by one. So let's start the discussion of the isomers with the stereoisomers, Lamai. So that is the part where the most questions will be asked, right? So first start with the enantiomers, then we can go towards the diastereomers. At the end, we can discuss about the constitutional isomers, right? So let's start our discussion of the isomerism part with the stereoisomers, right? Okay. So in your note at the page number 2, the section is there about the stereoisomers, right? Let's start with that. Okay. Right, Lama. Let's start our discussion with the stereoisomers here, right? So as they have mentioned in the note, right, stereoisomers or the stereoisomerism is the existence of compounds whose structure differs from each other only in the orientation of bonds in 3D space. Differs due to the orientation of bonds in 3D space, right? So it is very important to note that the stereoisomers are with same structural formula, same atomic connectivity, right? Same connectivity, right? So, but differs only with the arrangement in 3D space, right? So that is also mentioned. That is what we have discussed so far, right? There are two kinds of stereoisomers then. See, here also they are explaining that we have two kinds of stereoisomers. The first one is enantiomers, right? They are mentioning here what we have learned, right? Isomers which are mirror images of each other are called as enantiomers, right? Right? So when it comes to enantiomers, you clearly see the appearance of carbon atoms with 4 different groups attached to that, right? So these are referred to as chiral carbons or the asymmetric carbons. The carbons with 4 different groups attached to that, right? So if such a carbon is there in your compound, you can say that enantiomer appears with that, right? Some mirror image is there with the same molecular formula but with a different connectivity. So enantiomer appears if such a chiral carbon is appearing in your compound, right? What is a chiral carbon? It is a carbon with 4 different groups attached to that thing, right? chiral carbon. Sometimes it is referred to as asymmetric carbon. Right? Asymmetric carbon. Right? No? Okay. So basically, as I have mentioned, there are two forms now, D form and L form. Right? There are two. When it comes to mirror images, right? You have two components there. Right? Two components. Those two components are referred to as the T form and the L form. The D form and the L form. Right? Those are some names given to the two forms. Right? These guys are very identical, almost identical. 99% of it is identical, but differs only with the orientation of atoms in 3D space. Right? So those guys are named as D form and L form. Right? Okay. Just two names given for those. Right? Harada. D form L form. Right? Okay. So it's clear, no? Right. Let's go to the other things appearing with the note. Right. So in the note, the requirement to show the geometric isomerism is also mentioned. The requirement to exist in isomerism, requirement to show optical activity. Right, this process showing the isomerism is also known as showing the optical activity. Optical activity. Right, why it is referred so? The reason is these two forms, the L form and D form, can be only identified using the optical methods. Right? Only by using the plane polarized light. Right? So I'll discuss a bit more about that thing. So it comes D form and N form. This kind of a thing appears. Right? So I'll explain that thing a bit more. Why these things are referred to as this. Right? So as the atomic connectivity is the same, molecular weight, the atomic connectivity, kind of secondary interactions, all the things are same with these two guys, the two enantiomers, right? Because all the guys are same connectivity, same distances between the atoms, right? So same secondary interactions, same molecular weight, right? Molecular formula is same, molecular weight is same. So with all the other properties, with all the other physical properties, you can't differentiate these two guys. Even with the chemical properties, you can't differentiate the guys. Both are the same chemical properties as well. So what differs with these two guys is only the optical activity. Right? Optical activity, how they behave in the presence of light. This is the idea here. Right? To differentiate these two guys, we can use the plane polarized light. Right? So it is referred to as plane polarized light. Plane polarized light can be used to differentiate these two guys. What this means, what this plane polarized light means, like this now. Right? If you are think of a if you are referring to a light beam, right? If you are thinking of a light beam, various radiations are coming. They are beam of light. So with one wave, its axis could be like this. With another wave, axis could be like this. With someone be like this. Like this, rotation axis. Right? So some waves are coming like this, some are coming like this. Rotation axis changes, right? Like this. So, right, with various light beams, waves, you are with various rotation axes. Right? So plane polarized light means if you are to direct this kind of a beam through a very thin slit like this, what will happen? Only one kind of polarized light will come from here. If the one only with this kind of axis of rotation will comes out, only with this axis of rotation, not the others. And this is referred to as the plane polarized light. Radiation with only one kind of polarization will comes out, not the others. Others will stop. These things will stop. Won't be able to come through the slit here, right? This called a slit, thin slit, right? So then let's discuss how to differentiate the two guys, right? So if you are to pass this plane polarized light through your sample, let's say this is your sample, optical active sample, compound containing sample, right? If you have to pass this thing, two kinds of observations are possible. Sometimes, right? So it's like this. I'll write like this. After passing through this sample, right? Right, this radiation will come out, right? Two types of things are possible with this. Sometimes the radiation comes out after interacting with sample would have this kind of a rotation of the axis, rotation axis. Started with this and axis has rotated. Or this kind of rotation is possible. Right? If it is rotated clockwise, it is referred to as a D form. The optical active compound here is referred to as a D form. If the rotation is kind of anti-clockwise rotation, it is referred to as the L form. That is the only way of differentiating the optical active or the enantiomers. Right? This compound will rotate the plane polarized light clockwise, and this will rotate the plane polarized light anti-clockwise. Right? That is the only way of differentiating the two compounds. Other than this method, you can't differentiate the two guys. Both are giving you the same melting point, same boiling points. The chemical properties are same, right? Densities, all the stuff are same. Only these two guys only differs with the rotation of the plane polarized light, right? Only with the optical activity these two guys can be differentiated, right? So this is referred to as optical activity, right? Okay. So let's go to the note here, right? So that is what is mentioned here. Requirement to exceed the initial requirement to show optical activity, that is the optical activity, right? So and these are referred as optical active compound, right? Okay, the idea is clear, no? So to show this optical activity, your molecule should have a chiral carbon or asymmetric carbon, or one can say asymmetric carbon. What is an asymmetric carbon? sp3 carbon with 4 different groups. Four different groups attached to it. Such a carbon is referred to as an asymmetric carbon or chiral carbon. If you are with such a carbon, definitely you have a mirror image which is not the same compound, right? So those that guy and the mirror image is referred to as enantiomers. Got the idea, no? Right? So this is all what you should know about the enantiomerism. So go to these things as well. These optical active molecules are, and their mirror images are, two different compounds, and they are said to be enantiomers of each other. They are not superimposable. They are not superimposable. That means you can't put the other compound at the same space as the earlier compound, right? Not superimposable. Solutions containing optical active molecules rotate, plane, polarized light. So you got the idea, right? Only with these molecules, right, you see that rotation, clockwise or anti-clockwise rotation can be seen only with these molecules which are with chiral carbons, right? Got the idea, no? Right. Okay. Let's quickly go to the next type of stereoisomerism, diastereoism. We can discuss about this thing as well. Let's quickly go to the note here, right? Diastereoism, right? First the definition, right? See, it says stereoisomers which are not the mirror images of each other are called as diastereomers. Geometric isomerism is one occasion where diastereoism is seen, right? Okay, that is clear. Let's come up with the geometric isomerism. See, this is the situation, right? In carbon-carbon double bond, due to the phi bond, the two carbon atoms cannot freely rotate. Two carbon atoms cannot freely rotate. Why it can't be done? Due to the presence of the phi bond. In the presence of phi bond, two carbon atoms cannot be freely rotated about the phi bond, so that the geometric isomerism appears, right? So you can't rotate the two carbons, right? So that this compound and this compound, these two compounds are referred to as two different compounds, right? So I wish you got the idea. It's like this now. So if you are not with this phi bond, if you are not with this phi bond, the scenario is different. Why I am saying so? It's like this now. See. So if you are thinking of this kind of a compound, see, I must say, right, I must say this and this. I must say these two are the same. You can say these two are the same. Why is that? The thing is, we definitely know around this single bond, right, you can freely rotate you can freely rotate these two carbons. There's no phi bond to break here. So if this kind of a rotation occurs, this hydrogen comes to here, chlorine comes to here, and this molecule will be formed. So these two are the same compound, not two different compounds. Right, with the use of thermal energy available in your system, in room temperature also thermal energy is there. So if you see this one, and after some time if you are seeing this one, both are the same molecule, not two different stuff. The same compound has rotated to come up with this. So this can be rotated to come up like this as well. Right? If you have to come with this, right, it will give you this. So around a sigma bond, yes, you can rotate without breaking any of the bonds of the compound. Right? But when it comes to a double bond, when you have a double bond like this, if you are trying to rotate like this, what will happen? The double bond will break. The double bond will break. That is why it says, due to the phi bond, two carbon atoms cannot freely rotate. Two carbon atoms cannot freely rotate like this. So that this is not made by rotating this one. This is not made by rotating this one. This won't give you this. So that means this is just a different compound. This is just a different compound. This is not produced due to the rotation of this thing. That can't happen due to the presence of the phi bond. It will break, right? So these two are two different compounds there. So that the geometrical isomerism appears because of this. Due to the phi bond, two carbon atoms cannot be free rotate. That is why this kind of isomerism appears. Right? Got the idea? No? Right. Okay. So let's see what else they are saying. These two are two different compounds and called as dash unimers or geometric isomers of each other. They are not superimposable. You see, you can't put this one on top of the other. You can't occupy the same space, right? So requirement to show the geometric isomerism. The requirement to show the geometric isomerism. Let's discuss the requirement to fulfill to show this kind of a geometric isomerism, right? The requirement is this, Lama. Definitely there should be a double bonded carbons. There should be two double bonded carbons, right? So these are the two double bonded carbons, right? The requirement is this, Lama. The two groups attached to that carbon, the two groups attached to each of the double bonded carbons should be different. If you're taking this double bonded carbon, carbon 1, the two groups attached to that carbon should be different. Two groups attached to that carbon should be different. If you take this carbon, right? If you take the other double bonded carbon, two groups attached to that thing other than double bond also should be different. If this kind of a relationship is met, such a guy can show some dash unison, geometric isomerism, right? See what they are saying. The two groups attached to each carbon atom of the double bond, each carbon atom of the double bond should not be identical, should differ. The two groups with this carbon, one of this carbon should be differ, as well as the two groups of the other carbon should be differ when considering the two carbons of the double bond. If that requirement is met, then you can say yes, that molecule can show the dash unison, right? So then we have some special forms. Right? It's like this, right? So first of all, I am again telling you what we have said was two groups of each carbon should differ. But you can have the same group and here. So A and P can be same, E and P can be same, right? B and Q can be same. No worries with that, right? That could occur. But you can't have A and A. You can't have P and P. Sorry, P and P. Like that. So A can be equal to P. B can be equal to Q. Right? That is okay. But A can't be equal to B. Right? Okay? The idea. So if I think of this, right? Let's copy this, right? So there could be a situation like this. So you can have A and B here. Instead of P and Q, still you can have A and B like this. No worries. Right? Even like this. A and B, B and A. Right? So what this says is, actually, what this says is, this part says is actually, what they are saying is, if A is equal to P, A is equal to P, or B is equal to Q, that means if the same group appears at the same side of the double bond, if the two similar groups appears at the same side of the double bond, then that form is referred to as the cis form. Cis form. Right? Cis form. If the two same groups appears at the different sides of the double bond, such a form is called as trans form. Right? So these two forms are some special forms of geometric isomerism. The cis and trans appears only when one group of this carbon is also there with the other carbon as well. If one group appearing with one carbon is also there with the other carbon as well, you could see the presence of cis and trans isomers. Right? Okay. There could be instance without such a situation, right? See? So not all the geometric isomers comes under cis and trans. See? This kind of situation. You can have kind of a molecule like this, no? H is there, Br is there, Cl is there, CH3 is there. If you are referring to this thing, see, with this carbon, two groups attached to it is not the same. So this carbon passes the test. With the other carbon of the double bond, two groups attached to that thing differs. So this carbon also passes the test. So as both the carbons are fulfilling the requirement, we can say this molecule shows diastereoism, or one can say geometric isomerism. Geometric isomerism. Diastereoism as well, right? But you won't see the cis transforms appearing with this thing, because you don't have the common groups common to both the carbons. You don't have any groups common to both the carbons. But no cis trans situation here. So then if someone is asked you to come up with the geometric pattern of this thing, so if someone is asked you to come up with the geometric pattern, how to write that thing? Write in a geometric pattern. How to come up with the geometric pattern? It is very easy, Lamai. Just write one carbon, the first carbon, as it is, and then what you need to do is, with the other carbon, write the two groups by changing the positions. So you can add the CH3 here. You can write the Cl here by changing the positions, right? Just write. Okay. So it is how you are supposed to come up with the geometric pattern, right? Anyway, these are not referred to as cis-trans, right? Because you don't have any common groups with both the carbons. Common groups should be there with both the carbons to consider them as cis-trans forms, right? Both are geometrically active, right? This is geometric pattern of this one, and this one is geometric pattern of the other one, right? But no cis-trans forms. So not all the geometric isomers are cis-trans. There are geometric isomers without the cis-trans forms as well, right? Consider that as well, right? Okay, right. Let's see what else they are saying here. Sorry. Right. Okay, no? Yes. This is what I mean by the cis-trans forms. Right. So that is all you should know about the stereoisomerism part, right? So that is clear, no? Right? We had discussed about the enantiomers as well as the diastereomers, right? Let's quickly discuss about the constitutional isomers as well, right? We are planning to complete the theory part here, and at the next class we'll do the problem solving part, right? Okay, so let's quickly discuss about the constitutional isomerism or the chain isomerism, sorry, structural isomerism, right? See what are the things appearing here. So structural isomerism is of three parts, right? As mentioned here, it says the constitutional structural isomers that differ from the order in which the constituent atoms are connected. The atomic connectivity differs here. Those are referred to as structural isomers or the constituent isomers. Those are of three types. First type, the chain isomers, right? So with the chain isomers, right, the atomic connectivity differs due to the change in main carbon chain, right? Due to the differences of main carbon chain, right? Your structure changes, right? That is why such isomers are referred to as chain isomers. The name carries the meaning, right? Chain isomers. Due to the changes in the main carbon chain, right? Your structure differs, right? So chain isomers are those which have different hydrocarbon chains for same molecular formula. Right? Let's try to come up with such, right? So chain isomers, right? So for C5H12, so we can come up with different chains here, right? See, so C5H12 being an alkane, right? So all the 5 carbons could reside like this in a single straight chain, right? All the 5 carbons could be like this, 4 carbons with the straight chain and 1 carbon as a branch, or 5 carbons could appear like this, only 3 carbons at the longest straight chain, 2 carbons as branch. So all these forms are represented in the C5H12 molecular formula. So I am just writing the hydrogens to complete the 4 bond situations with these carbons, right? So 1 bond appearing, this means 3 hydrogens are needed. 2 bonds with this carbon, that means 2 hydrogens are needed. 2 bonds with this carbon means 2 hydrogens are needed. 2 bonds means 2 hydrogens, and only 1 bond with this carbon means 3 hydrogens are needed, right? This is your C5H12, right? For these things also I just complete the hydrogens to give the carbons the 4 bond situation. Right now, okay, with this one as well. These carbons are connected to only 1 bond, so 3 hydrogens are needed to give the 4 bond situation. No hydrogens are needed for this central atom, so as with 4 bonds there. So these are referred to as chain isomers. Some examples for chain isomers. You clearly see what differs here is the number of carbons at the main carbon chain. Here you are with 5 carbons at the main carbon chain. So it is kind of a pentane here we are referring to. It's kind of a pentane. Right? 5 carbons at the main carbon chain. When it comes to this one, it is kind of a 4 carbons at the main chain, the longest chain. So it's a butane. So one can write it as the 2-methyl butane. Anyway, number of carbons is 4 there at the main carbon chain. Bute, it's a bute, right? Because this one, its name is going to be just like 2,2-dimethyl branches, right? Only 3 carbons in your chain, that means propane, 2,2-dimethyl propane. So only 3 carbons appear at the main carbon chain. So due to the difference in number of carbons at the main carbon chain, right? These 5 carbons, pentane, butane, 4 carbons at the main carbon chain, propane, 3 carbons at the main carbon chain. Due to the difference of number of carbons at the main carbon chain, right? Their structure differs. Even in the same molecular formula, different structures. That means different molecules, right? So these are the chain isomers. You can clearly identify the chain isomers by just looking at the number of carbons at the main chain. This term will represent the difference between the chain isomers, right? Okay, right. That is about the chain isomers. Let's quickly come up with the next kind of isomerism, the position isomers. Right. Position isomers. So as the name suggests, right, this is the isomerism happens due to the change in positions. So it could be due to the change in positions of the substance group, or it could be due to the change in positions of the major functional group, main functional group, or it could be due to the position changes in the unsubstitution as well, the 5 bonds as well, right? So see, it says with the position isomers are those which have the same functional group and the substituents in a same functional group and or substituents in different positions in the same carbon chain. Different positions in the same carbon chain. See? So carbon chain won't change, but position will change. Of what? Of the functional group, or it could be about the substituents. Right? See some examples. See these examples. Right? So some examples appear at the bottom. See those? See? So here you clearly see the main carbon chain won't change. Prop, it's a prop. 3 carbon chain, it's a prop that won't change. Right? Functionality also won't change. But what differs is actually what? The position. The position, that is what differs. See the position. Position of the OH connected. The carbon number of the OH connected. Right? That is what differs. Position of the OH connected. At the one, the OH is connected. Here, at the second carbon, OH is connected. So, position of the functional group connected. The position of the unsaturation, the 5 bond between the 1 and 2 carbons. Here between the 2 and 3 carbons. The smallest number is written. So only that differs. It comes to position isomers, right? You clearly see only the position of the substituent group or the major functional group or the unsaturation will differ. All the other things of the name appears as it is, right? See, butane, this is also butane. So position of the main carbon chain, where you're interested, functional group or the unsaturation or substituent group appears, will change here. The carbon chain is the same. Both are propane in this case. In this case, both are butane. But these two are position isomers because the position of the triple bond changes, and these two are also position isomers as the position of the major functional group changes. Right now, so that is, those are the position isomers. Name carries the meaning, right? Okay. Let's quickly discuss about the last type of isomerism. Right? This is referred to as a functional group isomers. Right? Functional group isomerism, the third kind. Right. As the name suggests, the functional group isomerism means that should be a difference, right, of the functional group. That the isomerism should occur due to the difference of a functional group, right? So that is what happens here. The structure will differ due to the difference of a functional group, right? Such major 3 examples are there. Let's go through one by one. First of all, let's go to the definition here. Functional group isomers are those which have different functional groups in compounds having the same molecular formula. So for to be an isomers, definitely the molecular formula can't be changed. So in this case, the difference happens with the functional group, right? See some of these examples. Basically, alcohols and ethers coming as functional group isomers. See these examples. C3H8OH. So if you have to think of the 1-propanol, see, this is an alcohol, right? if you think of this thing, this is an ether, right? This guy is kind of alcohol, this is kind of ether. Both are coming up with same molecular formula. You have 3 carbons, 8 hydrogens and 1 oxygen. Even here 3 carbons, 8 hydrogens and 1 oxygen. The alcohols and ethers are a good example for functional group isomers, right? This is just about another example, the aldehydes and ketones. Another good example. See, the aldehydes and ketones. So consider this aldehyde, 3 carbon aldehyde, and this ketone. So you clearly see both of these compounds are with 3 carbons, 6 hydrogens and 1 oxygen. Even with here 3 carbons, 6 hydrogens and 1 oxygen. Both are coming up with the same molecular formula, but 2 different compounds. This is kind of aldehyde, this is a ketone. These two guys diverse due to the difference of major functional group. See, this is an aldehyde, this is an ketone, right? So aldehydes and ketones are a good pair. For an example, for a functional group isomerism. This is how the carboxylases and esters. It is also a good pair in coming up with the functional group isomerism. See, the carboxylic acid. Copy this carboxylic acid. See, 3 carbon carboxylic acid, propanoic acid, and take this one as well. This ester, right? You clearly see with both of these compounds 3 carbons, 6 hydrogens and 2 oxygens appear. 3 carbons, 6 hydrogens and 2 oxygens appear. But those are 2 different compounds. Why is that? Due to change in their major functional group. This is a carboxylic acid. This is ester. This is a carboxylic acid. So carboxylic acids and esters are a good example for functional group isomerism, right? So due to the major functional group, difference in the major functional group as well, you can observe the presence of isomerism, right? No? Okay, that is all about the theoretical part regarding the isomerism, right? So we'll discuss how these concepts will be used in problem solving at next day. Our next day's discussion will be greatly focusing on the problem solving techniques with use of isomerism. For the questions appearing with the isomerism, basically you should know about the admission tests as well for these compounds. So just go to those as well and join me in the next lesson, right? So until then, goodbye. See you next day.